Okay, in this problem, we are going to find the deflection of this bar that I have here over at point B, over at the right side of this. Okay, so the first thing I need to do is figure out basically the moment in each section. I'm going to cut between each of these. Before I do that, I've got to figure out the reaction forces that I have here. So if I sum the forces in the y direction, I learned that the reaction at A is just P going down. Okay. Then if I sum the moments, I can find that the moment over here is going to be PL over 2, and that keeps it again in static equilibrium. Once I know those two things, I can cut on each side of the P. Okay, and I figure out what I have here is I have two coordinates. One goes from A to the right, one goes from B to the left. That's x1 and x2. Okay, so I can find the moment of x1 equals P times x1. And the moment of 2 just equals PL over 2. And again, one is coming from A over to the right, one is coming from B to the left. Okay, so starting with x1, I know the moment is px1, and what I do is I just integrate this twice. Okay, setting that equal to EI times the second derivative of the elastic curve. So I integrate it twice, so I get px squared over 2 plus an integration constant. Integrating it one more time, I get px squared, that should be cubed, px cubed over 6 plus c1x1 plus c2. Again, there's a little typo here. That should be px cubed. Okay, now doing x2, okay, again, m2 is just pl over 2. So then taking two integrals of that, I get pl over 2 times x plus a constant. That should actually read C3. There's another typo here. That should be C3. Okay, it's correct down here. When I integrate it one more time, I get PL over 4 x squared plus, again, that's C3 times x plus C2. So again, these equations are all based on x2, which is moving from B to the left, and the top equations are for x1, which is from A to the right. Okay, so I've got my equations. Okay, but I've got 4 unknown constants here, so this is where I start applying boundary conditions. And what I know is at point A, which is where x1 equals 0, I know my deflection has to be 0 because it can't go through this roller. So at this point it equals 0. So I use the equation for the deflection. Okay, set that equal to 0, set x1 equal to 0. And I basically find out that, well, for that to occur, C2 has to equal 0. So I've got one of my constants. The other thing that I know is over at B, the slope has to be 0 because of the way this thing is rigidly, well, it's not rigidly fixed, but it can't rotate here. Okay, so dv dx, when x equals 2, has to equal 0. Again, because I'm going from B to the left. Okay, so then I use this equation right here, okay, where I plug in x2 equals 0, okay, dv dx 2 also equals 0, therefore, again, the typo here, this should read C3 equals 0. Okay, and again, that's because the slope over at B is 0. So C3 has to equal 0. So those are my two boundary conditions. Now, the other thing that I know is right at the middle of the beam, where basically both x1 and x2 both equal L over 2. Again, I'm going, x1 goes from A to the center, and B goes from B to the center, or x2 goes from B to the center. So when those both equal L over 2, okay, again, the continuity has to be there, which means that the deflection has to be the same because the beam can't just all of a sudden jump to a new point, as well as the slope needs to be the same. Now, the slope of 1 equals negative the slope of 2. That's because the fact that, my slope is rise over run. Well, my run for x1 goes to the right. My run for x2 goes to the left. So that's why we have that sign difference there. Okay, so basically I know the equations, the displacement equations have to equal one another when x1 and x2 equal L over 2. So that's what I've done here is I've plugged in L over 2, okay, where I see x. That another typo here. That should be L over 2. Yep. Okay. As should what I have here, where I plug in L over 2 for x2. Okay. Okay. So this next equation I have here is the fact that the slopes have to equal negative each other. So I plug in, again, L over 2, okay, for x1, and I plug in L over 2 for x2 in the slope equations and set it equal to one another. So that's where this negative sign comes from. So from this equation, I can find that that constant equals negative 3/8 PL squared. Taking that, plugging it into the equation above, I get negative 11/48 PL cubed. Okay, recognizing lots of typos here, but hopefully you're following this, where I use these boundary conditions and these continuity conditions to figure out these integration constants. Now that I've found all of these integration constants, I can actually find the deflection of point B simply by taking L over 2 and plugging it into the V1 equation. Or I could actually plug in L over 2 into the V2 equation, and I can get negative 11 PL cubed over 48 EI. Okay, so very long methodical process. Okay, find your moments. Okay, take a couple of integrals, then use boundary conditions, continuity conditions in order to solve for the integration constants, and then once I have those, I actually have an equation for my deflection that I can do what I need to with it.